Okay, so, whoops. Oh, okay. So, any other questions, concerns, any particular topic? How about you guys out there in Zoom? Any questions you guys have? No questions?
I do have a question. Would
Uh,
you be able to work out some of the problems for assignment number 5, but for the additional one?
okay, so let me, and somebody just typed in the chat, Miss Hersey was, I guess you're talking about redux, balancing redux equations, Miss Hersey? She's not responding. Oh, okay, good, okay. All right, so who was it that was talking a while ago? Was that Miss Macias?
Yes.
Okay, you were asking about what now?
The 3 questions from assignment number 5.
All right, let me see if I can bring this up on the screen. Canvas has been acting kind of weird. Assignment number 5. Okay, so you're talking about this assignment right here?
Yes.
All right, and any particular questions, or you just want me to start from?
I think I was able to do the first one, but the second and third one were the ones that gave me kind of issues. Like I wasn't able to,
Okay,
I
so
didn't know how to do them.
right, so for this, you're talking about determining the pH when you add a certain amount of base to an acid solution, and it gives you information about the acid, like in the case of A, 6 mils of 0.200 m benzoic acid, and it gives you the Ka value for the benzoic acid, and it gives you the volume of the base added, and you are to, oh, you walked me right up. And they give you the volume of the base and the molarity, all right? So what the first thing you'd have to do is, it's an acid-base titration type problem. So let me turn on my pen. I can, oh, not that. What am I doing? Okay, let's see. Okay, how do I get out of this here? How do I? Okay, all right, I think I'm in business now. So let me turn the pen on. Okay, so the first thing I would do is try to find a number of moles of both the acid and base, right? So the number of moles of the base, which is sodium hydroxide, that will be equal to the volume of the base, which I have to convert to liters. So 1 liter over 1,000 mils. And then I'll multiply that by the molarity of the base, which is 0.0500 moles per liter. And I would work that out. So let me get my trusty calculator here. So that is 12 times divided by 1,000. Oops. 12 divided by 1,000 times 0.0500. And according to my calculation, this works out to be 6.00 times 10 to the minus 4 moles. And then I do a similar calculation for the benzoic acid. I'm going to use HB to represent benzoic acid, right? So the volume given for the benzoic acid is 6.00 mils. Again, you have to convert that to liters, 1 liter over 1,000 mils. And then I'll multiply that by the molarity, which is 0.200 moles per liter. So let's see what that gives. So that's 6 times, or divided by 1,000 times 0.2. And this works out to be equal to 1.20 times 10 to the minus 3 moles. And then the next step would be to write down the balance equation for the reaction, which would be NaOH plus HB to give NAB plus H2O, NAB plus H2O. Now, you must always remember, if it's an acid-base reaction, like, sodium hydroxide reacting with HB, it's not going to be an equilibrium situation. The reaction is going to go to one direction, which means that the limiting reactant will be used up. So we're going to set up an ice table where initially the number of moles, excuse me, of the sodium hydroxide is 6.00 times 10 to the minus 4. The number of moles of HB we calculated to be 1.20 times 10 to the minus 3. Initially, we would have none of that, and we don't need to concern ourselves with the water. So, of course, because it's a 1-to-1 mole ratio, we can easily determine which of these two would be the limiting reactant, and that would be the sodium hydroxide. So all of it will be used up here. So the change for the sodium hydroxide will be minus 6.00 times 10 to the minus 4, and the same is true for the acid. And then as far as the sodium benzoate is concerned, the change here will be plus 6.00 times 10 to the minus 4 moles. So at the end of the reaction, you're going to have no sodium hydroxide. Here, you're going to have 1.20 times 10 to the minus 3 minus 6.00 times 10 to the minus 4. And if I'm not mistaken, that would be equal to 6.0 times 10 to the minus 4. And this would be 6.00 times 10 to the minus 4. The next step, I'm going to see if I can squeeze it over here, is where we find the concentrations of what is left, which would be the HB and the sodium benzoate. And because the mole values are the same, right? Well, firstly, let me calculate the volume at this stage. So the volume of the solution at this stage would be the 12.0 mils plus the 6.00 mils, right? So that is 12.00 mils plus 6.00 mils, right? So that's going to be equal to 18.00 mils, right? So the concentration of HB is going to be equal to the concentration of NAB, or B minus, which will be equal to 6.0 times 10 to the minus 4 moles divided by 18.00 milliliters, which we have to convert to liters. So 1 liter over 1,000 mils is what you're going to multiply that by. And when you work that out, that's going to be equal to 6 times 10 to the minus 4 divided by. So according to my calculation, this is going to work out to be equal to 0.0333 m, right? Now, because the concentrations are, well, firstly, you must recognize that the two components, or the two components of the mixture present at this juncture would be a weak acid and the conjugate base of the acid, which means that basically we have a buffer, right? And when it comes to buffers, we can calculate the pH easily by using this equation. pH is equal to pKa plus log of concentration of A minus or B minus divided by concentration of HA or HB. So basically what we need to do is plug in the values of pKa. Now pKa would be minus log of the Ka, which is given here. So minus log of 6.28 times 10 to the minus 5. And then I'll add to that log of concentration of A minus over HA which would be, these two will be the same, right? Because of what we said here. So therefore, that will be log of 1. And of course, log of 1 is equal to? What's log of 1 equal to? 0, right? So therefore, all we have to do is find out what the log of 6.28 times 10 to the minus 5 is equal to. And according to my calculations, that works out to be equal to 4.20. And that will be the pH of the solution at that point. All right? Okay, any questions about this one? Any questions? Any questions? And it's pretty much a similar approach for the other parts. You have to pay attention to the numbers that are being used for the volume and molarities. And also, when you set up the table, you have to make sure that you follow the stoichiometry so that you can determine what remains at the end of the reaction. That is very important in terms of determining the pH, because like you see in this case here, at the end of the reaction at this point, the concentrations of both the acid and the conjugate base are the same, so therefore the pH will be equal to minus log whatever the Ka is. But if the concentrations are different or not the same, then you'd have to put those numbers into this equation here. And if you get to a point where, let's say, at this point here, you have only base and no weak acid or no conjugate base, then the pH will be based on the concentration of the base. So you'd have to find pOH first and then find pH after. So it all depends on what is the state of affairs when you get to the end of the reaction at a particular point in the titration. All right, yes, ma'am.
Why did we do that again? The part, like the part we did on the right?
Oh, you mean this here?
Yeah.
To be perfectly honest, it's not absolutely necessary, only because the concentration of the weak acid and the base, conjugate base, are the same. So once we know that to be the case, we don't really need to do this. But I did this just to make sure that you know how to do it, just in case that's not the case. You see what I'm saying? Because you might have a situation where the concentration of HB is something different from the concentration of B minus. In that case, then you have to work out those values and then you plug it into the Henderson-Hasselbalch equation to get the pH. All right? Okay, any other questions about this one? Any other questions? Because I want to get to the question that Ms. Hersey was asking about. She was asking about balancing redox equation. Do you have a particular question in mind or what, Ms. Hersey?
Can you hear me?
Yes, I can.
Can you hear me?
Yes, can you hear me?
Yes. Okay. No, I get how to do the equations. It's more of setting up the half equations. So whatever you could give for practice, that would be awesome.
Okay. I guess I'll just make up an example. Is it okay for me to clear this? All right, so let me clear this here. And let's see. Let me. Okay, so let me. Oh, what's going on here? Okay, why is this thing not? Oh, okay, now we're in business. All right, so I'm just going to make up an example, which I'm not really good at, but I'll try. Okay, so suppose you're given. All right, here's one. Suppose you're given this NO2 to form NO3 plus N2. All right. So in this case here, what you'd have to do is you'd have to, as we all know from the first step, we separate this into two half equations. So in this case, one half equation would be NO2 to form, I'm sorry, this should be NO2 minus and this should be NO3 minus, all right? Okay, so NO2 minus to form NO3 minus, all right? And then you can have NO2 minus to form N2, all right? So this kind of reaction, I don't know if I introduced this term to you guys, is called disproportionation. And basically what's happening in disproportionation is that you start off with one reactant, some of which will undergo oxidation and the rest will undergo reduction, right? So from here, we follow the steps, which would be that the next step is that we balance all atoms excepting oxygen and hydrogen, which we don't have to be concerned with here because in the case of the first half equation, the nitrogens are balanced. However, in the case of the second half equation, we have two nitrogens here, we have one here, so I'm going to put a 2 here, all right? Then the next step is that we balance the oxygens by adding water to the side that needs it. In this case, that means we add H2O to the left side. And in this case, we add 4 H2O to the right side, all right? And then to balance the hydrogens, we add H plus ions. We have 2 hydrogens here, so that means we need to add 2 hydrogen ions on the right side. And in the case of the second half equation, we have 4 times 2, 8 hydrogens on the left side, which means we need to add 8 hydrogen ions on the left side. So the next step is to balance the charges. And again, this is where students tend to make their errors. Remember, what you do is that you look at the total number of charges on either side, and then you add the appropriate number of electrons to the side with the higher net charge. So in the case of the first half equation, you have -1 here, total, on the left side, and then on the right side, you have +1 on the right side. So the question is, to which side do we add electrons and how many? And the answer is that we add electrons to the right side, and the number of electrons I would add to the right side would be 2 electrons, because by adding 2 electrons, I'm adding 2 negative charges, which will result in the total charge on the right side being equal to -1, which is the same as the total charge on the left side. So for the second half equation, we have a total of 8 minus 2, so that's +6 on this side, and on this side we have 0. So the question now becomes, to which side do we add electrons and how many? And well,
The left.
how many would you add to the left?
6.
6 electrons, exactly. So 6 electrons to the left, and that balances the charges. Okay, so now that we have balanced the charges, the next step would be to equalize the number of electrons. In other words, we have to ensure that the number of electrons lost in the oxidation half reaction is equal to the number of electrons gained. As it is right now, that's not the case. We have 2 electrons being lost here. We have 6 electrons being gained here. So what we do is that we take this equation here and multiply the entire equation by 3 so that we end up with 6 electrons. But of course, that means you have to multiply everything else by 3. So that becomes 3 H2O plus 3 NO2 minus. And then on the right side, you're going to have 3 NO3 minus plus 6 H plus 6 electrons, all right? And then what do we do next? We add up both equations. Of course, we cancel out those common items on both sides. The electrons would have to go. Remember, there should be no electrons left at the end of this process. So the number of electrons canceled out will be the same. Yes, ma'am?
So we don't multiply the second.
No, we don't need to, because once you you mean this equation here?
But
Because in this case, we don't need to, because once you multiply this by 3, we're going to end up with 6 electrons here, which is equal to the 6 electrons there, right? There's some other things that will cancel out also, namely, these 3 water molecules will cancel out 3 of these, leaving behind 1, and these hydrogen ions, 6, will cancel out 6 of these, leaving behind 2. So we're going to be left with 2H plus, and notice here now, we have 2 NO2 here, we have 3 NO2 here, so therefore 5 NO2 minus. And then on the right side, we have N2 plus 3 NO3 minus plus H2O, all right? And this should be the balanced equation, but of course, as I always say, at this point, you check to make sure everything is balanced. We have two hydrogens here, we have two hydrogens here, so they're balanced. We have 5 nitrogens here, we have 2 plus 3 nitrogens, 5. We have 5 times 2, 10 oxygens. We have 3 times 3, 9, plus 1, 10 oxygens. And then as far as the charges are concerned, we have plus 2, minus 5, which would be equal to minus 3. Here we have 3 times minus 3, so everything is balanced. Now remember, this is in under acid conditions. Right, what we just did. So you could be asked for this, but you could also be asked for the equation for the reaction under basic conditions. Yes, ma'am.
How do you get to two H plus?
Here, because these 6 H pluses cancel out 6 of these, leave behind 2.
Okay.
So therefore, we end up with 2 H pluses on the left side.
So what's on, for example, if you have something on the left side and if you have something on the right, you subtract those.
Right. You cancel out the common item on both sides. We did that for the electrons, we did that for the H pluses, and we did that for the water, right? So that's something you must always look out for. Okay, so let's say the question was asking for balancing, getting the equation for the reaction on the basic conditions. So the way we do that is we look at the number of H plus ions that we have here, and we add an equal number of hydroxide ions to both sides. All right? Now, of course, when that happens, these 2 H plus will react with these 2 hydroxide ions to form 2 water molecules. And then what's going to happen is that this water molecule on this side is going to cancel out with one of those. So your final answer, I'm just going to squeeze it in this box right here. The final answer is going to be H2O plus 5NO2 minus, and then on the right side, you're going to have N2 plus 3NO3 minus plus 2 hydroxides, and that would be the balance equation for this reaction under basic conditions. All right? Okay, yes, sir.
Why is there only one H2O on the left side?
Because you mean here?
Yeah.
Because this H2O here will cancel out one of the 2 H2Os here.
Oh, okay.
Right, so you'll be left with 1 water molecule on the left side as a result. Yes, ma'am.
Why do you do 20 H?
Hmm?
Why do you do 20?
No, this is
Oh,
2 OH minus. Yeah,
Okay.
sorry.
Are you, okay, no, that's fine.
Yeah.
You're trying to cancel.
So remember, what I did was that I add 2 hydroxide ions to both sides here and here.
Uh-huh.
When you add 2 OH minus to 2 H plus, you're going to get 2 water molecules.
Okay.
And then, as in answer to his question, this water molecule here will cancel out one of these 2 water molecules.
Okay.
So that's how we end up with 1 water molecule here. All right? Okay, any other questions concerning this example? Yes, sir.
On the test, will yeah, if we want to solve for acid conditions or basic conditions?
Yes, I will be specific. I'll ask if it's acidic or basic conditions. So in the case of acidic conditions, you stop at this point right here. And then in the case of basic conditions, you add your OH minus appropriately to get the basic condition equation. Okay, so Ms. Hersey, I'm not sure if I answered your question to your satisfaction. Please let me know. Or if there's any other question you guys have. Oh, let me see. Oh, okay, you're welcome.
In assignment number 7, but the additional ones.
Okay, hold on
Yes.
1 minute. See if I can bring this up on the screen. Number 7. Okay, which question?
The ones that have to do with cathode and anode, like having to distinguish those. For example, I think one of them is number 9.
Number 9. Oh, so I think I know what you're talking. Oh, hold on. Oh, there's an additional. Hold on, let's see here. Where did I post that? The addendum, okay. I think I know what you're referring to. You're referring to this here?
Yeah.
Okay. Now for this one, you're gonna need a table. Okay, let me download this here first. And then let me get to the table. So the table you're gonna need is, where is it? Tables. Which you'll have access to, of course. Download that as well. Okay, so this is the table you're gonna need for answering the questions in that. Okay, so let me go here. And let me make this larger. Okay, so the question starts with, in an electrolytic cell, the negative electrode is negative because it has, of course, too many electrons. And then chemicals that will come into contact with the negative electrode will gain electrons and be reduced. The negative electrode in electrolysis is called the cathode. And the question is asking, write the change that water undergoes through at the cathode. And the answer to that is, come on. Okay, so the answer to that would be water plus electrons to form OH minus plus H2. And of course, to balance that, we're gonna need a 2 here, a 2 here, and I think a 2 here. That's it. So that would be the reduction of water to form hydroxide and hydrogen. And then in number 3 says an electrochemical cell. The positive electrode is positive because it has too few electrons. The chemicals that come into contact with that electrode will lose electrons and be oxidized. And the positive electrode in electrolysis is called the anode. And the question is asking, write the change that water undergoes through at the anode. And that's an oxidation reaction where water will form hydrogen ions and O2 plus electrons. And to balance this, we're gonna need a 2 here, a 4 here, and a 4 electrons here. So that would be the equation for the oxidation of water. Right? Okay, so continuing, let me I think it's okay for me to clear this, right? All right, so let me clear this. And let me scroll down. It said add these 2 equations together. Oh, make certain. Okay, so let me just rewrite the equations that I just deleted. So one equation is 2H2O plus 2 electrons to form 2OH minus plus H2. And the other equation is the oxidation of water, which forms 4H plus O2 plus 4 electrons, and I need a 2 here. Okay, so to balance this, or to add these two together, we have to make sure that the number of electrons gained and lost will be the same. So what I would do is multiply this by 2. So that would give 4 H2O plus 4 electrons to give 4 OH minus plus 2 H2. And then I would add these two equations together, and I'm going to end up with 6 H2O. On the left side, these 4 electrons will cancel with those 4 electrons. So you're going to end up with 4H plus 4OH minus plus O2 plus 2H2. Now the thing is that these here, the 4H plus and the 4OH minus will add to form 4 water molecules, right? So these 4 water molecules will cancel out with 4 of these, leaving behind 2. So your final equation will be 2H2O to form O2 plus 2H2. So this will be the final answer right here. All right? Okay, any questions about this? Any questions? Any questions out there in Zoom? Okay, so let me clear this and scroll down. Okay, so this is where we're gonna need a table. I wish I had a split screen kind of situation. Let me see if I can work on something here.
You need this like split.
Let me bring this down like this and do this. Oops. Let's see here. Okay, I think this can work. So the question is, we will perform this electrolysis using an aqueous solution of sodium sulfate. Both the sodium and water will be near the electrode, which is the cathode. Which chemical is more likely to be reduced? So what we have to do is look at the equations potentially for the reduction of both water and sodium. In the case of sodium, Na plus electrons to give Na would be the potential reduction reaction. And in the case of water, as we saw before, H2O plus electrons to form OH minus plus H2. And we multiply right through by 2. Okay, so what we have to look for are the standard EMF values for both sodium and water reduction. So that means I have to come over here. Okay, so what I'm going to be looking for is the EMF value for sodium reduction, sodium ion reduction. Okay, so here's the value for sodium ion reduction. So that is equal to minus 0.271. So let me write that down here. This will be equal to minus 2.71 volts. And then I look for the same value in the case of the reduction of water. So I have to look for that equation here. Okay, reduction of water. Oops. Yeah, this is the part that is kind of, oh, here it is. Okay, so the EMF for the reduction of water is minus 0.83 volts, right? So what we do is compare these two and ask ourselves the question, which one is of a higher value? The one that is higher in value is the one that's more likely to occur, right? So when we compare these two, we see that this is more likely, this is higher. So therefore the answer is that the one that's more likely to be reduced would be the water at the cathode. And that's it, right? So that's how you determine which of the two substances attracted to the cathode will undergo reduction, all right? Now, in the case of number 7, it says both the sulfate and water will be near the positive electrode, the anode. So it's asking for which of these two would be oxidized. Yes, ma'am.
For 6, how do you know which one to use, given that you have several equations to start with?
Well, you look for the one you're talking about this one right here? Right. So basically you look for the one that involves the reduction of water that we saw earlier. Remember the questions I answered earlier?
Okay.
Right, that's the equation you're gonna look for,
Okay.
right? So for the reduction of water, that's that. Okay, now in the case of number 7, it's oxidation that you'll be concerned with, right? Now, we already know what the equation for the oxidation of water is from the previous part, right? That would be H2O, to form 2H plus O2 plus electrons, and to balance this, we need 2 here. This should be 4, and this will be 4 electrons, all right? So we need to look up the EMF value for that. So let me see if I can find that over here. Now, here's the thing about answering this question. The equation that I have written here is for oxidation. All these equations that you see in the table are reduction of equations, right? So basically what you'll be looking for in order to find the EMF value for this equation is the reverse, right? And I think I found it right here. All right? If you look at this and look at what we have here, this is the reverse of this, right? So what does that mean for this? The standard EMF would be minus 1.23 volts, right? So you have to be careful when you're using these values. You have to make sure that the standard EMF value that you're going to use is for the equation as it is written. That equation might be written in the reverse in the table, in which case you have to change the sign in order to get the EMF value of that particular equation. Now for the sulfate equation, oxidation, I'm not sure what that is, so I'd have to look it up in this table. So what I'm going to do is, okay, in fact, it's right here, I think. Here it is. The sulfate, no, wait a minute. I'm looking for the sulfate undergoing oxidation. So this would be what I would use right here. Right, this is the reverse, okay? So that equation, the reverse equation we'll be looking for is this, for the oxidation of the sulfate ion to form S2O8 2 minus plus 2 electrons. And the EMF value of that would be the negative of what this is, which is 2.05, so minus 2.05 volts, right? And again, I'll compare the two EMF values, and the one that's more positive is the one that is more likely to occur, which means that water, again, will be the species that would be more likely to be oxidized at the anode. If you have water and sulfate at the anode, water will be the one that will be preferentially undergoing oxidation. All right? Okay, any questions about that? Any questions? Any questions? Any questions out there in Zoom? If not, let me move on to number 8, which says that the electrolysis of potassium iodide, both the potassium and the water, both the potassium ion and water will be near the electrode. So again, it's kind of similar to what we did here. Now, I'm just going to rewrite this here because it's the same water that we'll be using. So I'm just going to rewrite here 2H2O plus 2 electrons to form 2OH minus plus H2, and the EMF value of that is minus 0.83 volts. Now, what I have to look up in the table is the EMF value for the reduction of K plus to form K. So that's what I'm going to look up over here now. So let's see if I can find it. Oh, here it is right here on the same page, luckily for us. So this is what I'll be, what I just found. So the EMF value is according to the table, minus 2.93 volts. So of those two, the water or the potassium ion, which one is more likely to undergo reduction at the, cathode? Water, so the answer here would be H2O, all right? Okay, any question about that before I move on to the next page? So, let me clear this here. And let me scroll down. Okay. Or remember, I didn't provide enough space to do this part here. But anyway, both the I minus and H2O will be near the plus electrode, right? So I'm just going to continue that. I'm going to do this part here up here, right? So in the case of water, we already know what the equation is. H2O will give 2H plus, I'm sorry, I keep saying 2. This should be 2 here. This should be 4H plus O2 plus 4 electrons. And since I'm lazy, can somebody remind me of what this EMF value is for the oxidation of water? We did it earlier.
Negative 1.2.
I'm sorry, minus
1.2.
1.2? Was it 1.23?
Yeah.
Okay, all right. And then now I do have to look up the value for the reduction of I minus. So let me see if I can find it over here. This table. I minus undergoing oxidation. Oh, wait a minute. Wrong equation. It's reduction. Let me, I'm sorry about that. I just realized that I should be writing down the reduction equation here. So the reduction equation is H2O plus 2 electrons to form H2 plus OH minus. So that would be 2, and that's it. And the EMF value of that was what?
Negative 0.83.
Minus 0. Hold on, I think I probably did the wrong thing. Okay, let me do this one first and then go back to what I think the error I made was in the earlier question. Sorry about that. So what I have to do now for this question is look up the I value. So let me see if I can, the value, the E value for the, you know what? I'm confusing myself. What I'm doing here is for the question that we did already. What did I say the answer was for number 8? For this part right here, what did I put here?
H2O.
H2O, right? And the values I used for the reduction of water was this in that question, right? Was it?
Yeah.
Okay, all right. I'm confusing myself. Let me just erase this here. I was right earlier. I need to focus on down here and not up there, all right? So I minus H2O undergoing oxidation, right? To form 4H plus O2 plus 4 electrons, right? 2 here. And then the I minus will undergo oxidation to form I2 plus 2 electrons, right? So what's the EMF value that I had for the oxidation of water? If I'm not mistaken, that's minus 1.23, right?
Yes.
Minus 1.23 volts. And then for the oxidation of I minus, that's what I have to look for right now. Okay, so let me see if I can find that in this table here. Here it is, right here. Now this here is the reverse. So the value I'll be looking at here is for the standard EMF, that will be equal to minus 0.54 volts, right? Okay, so compare these two, which one is higher? Which which one of these two would be of a higher value?
Negative 0.54.
Minus 0.54. So therefore, the I minus would be the one that would be more preferentially oxidized at the anode. Yes, sir.
Would you go put a 2 in front of the I minus?
The two in front of the what?
Would you put a 2 in front of the I minus for a coefficient? Because it's.
Oh, yeah, sorry, my bad, yeah. Yeah. So, oh, actually, space is provided here. So this here, the I minus undergoing oxidation would take place at the anode. So let me just rewrite that down here to form I2 plus 2 electrons. And the reaction at the cathode would be the reduction of water, H2O plus electrons to form OH minus plus H2. And this is going to be 2, 2, and 2. And then the next question is, what's the overall equation? Basically, just add these two. You're going to end up with 2 H2O plus 2 I minus to give 2 OH minus plus H2 plus I2. And that would be the answer for that. All right? Okay, do I need to continue with the rest of these, Ms. Macias, or?
No,
All right, yeah, once you understand what we did previously, pretty much is the same process for the others, all right? Okay, any other question? What time is it? Okay, we have time. Any other questions? Any other questions? Any other questions from you guys out there in Zoom? I think what I'll do, today's what? Today's Wednesday, right? So in addition to the office hours that I'll normally keep for the rest of the week, I think I'll make myself available over the weekend. I'm not sure yet. I'll let you guys know by announcement whether or not it will be Saturday or Sunday, but from the look of things, I think it would be on Sunday evening. So I'll make sure that I make myself available on Skype once I have determined what time exactly and what day exactly I'll be available. If you have any questions, any last minute questions.
so you said that, what should we go over, like practicing again and again?
The assignment that are numbered. No, I think because I remember Mr. McKinnon asking me about past test questions, which I think I've published, if I'm not mistaken.
Yeah.
Let me see. Let me clear this first. Avoid the confusion. Okay. So yeah, assignments, what did I say? 5, 6, and 7, right?
Yeah.
Okay, and I think I've posted some past test answer keys. Let me look here. So let me see what's in store here. Test number 3. Okay, so this is download it. Whoops, wrong download. Okay, so Let me see, I just wanna check the topics here. Okay, so this is a case B problem. This is another case B problem. And this is a titration like the one that we did just now. So you may want to review that. Okay, so that's one, and then this other one here, down here. Okay. Oh, this is some additional questions to that test also. So this is the formation constant problem. And this is a case B problem. So yes, so I would review these two. All right, in addition to reviewing your assignment questions. Let me check out this one here. This is another test number 3, answer key. Let me see here. Let me see what this one has in store. Oh, it's upside down. Okay, let's see here. Okay, thermodynamics, entropy. So I would review this as well. Free energy, balance and redox equations in both basic and acidic conditions. So, and electrochemistry, standard EMF, electrolysis, yep. So, well, nuclear chemistry, no. That would be the final, however. So you can review that for the final, but not for this test, right? So let me see here. And that's it. Yeah, so pretty much on this paper, everything except nuclear chemistry would be covered on the test, all right? So I would review, if I were you, I would review these test answer keys, all labeled test number 3, but in this one, just ignore the nuclear chemistry questions for now, because that would be on the final, definitely, all right? So that's basically, if you review those, as far as I'm concerned, you should be in good shape for the test. And the assignment keys, of course. All right? Any other questions? Any other problems, issues? If not, how about you guys out there in Zoom? Any questions? If not, that's pretty much all I have for you today. But of course, feel free to contact me during office hours. And as I said before, I'm going to set aside some time this weekend so that you guys can call me if you have any questions. All right? Cool. Yes, sir. Oh, longest chain again, huh?
This one.
Oh, okay. Well, let me see here. The longest chain is 1, 2, 3, 4, 5, 6, 7. Okay, so the pyridine is heptane. This is on carbon number 2. That's a methyl group, by the way, not ethyl. So that's carbon number 2 and carbon number 4. So it's 2,4-dimethyl. What is the longest chain again? Heptane. No, hexane.
And that's how it goes?
1, 2, 3, 4, 5, 6. Oh, heptane. Okay, so yes, 2,4-dimethyl heptane. Alone. Four, 5, 6, 7, 8, 9. So that's not it. Okay, so
See you in 5?
yeah. Okay, so I would count this way because ethyl comes before methyl. So, it's going to be 4 ethyl, 6 methyl, none, yeah, that's correct, yeah.
And then for this one, will it be 3 ethyl?
Let me see. 1, 2, 3, 4, 5, 6, 7, so that's heptane. 1, 2, 3, 4, 5, 6, 7.
So that should go.
Yeah, so the parent name is gonna be heptane. And let me see here, so 1, 2, 3, 4, so that's 4 ethyl heptane, yeah. So take out the 3 methyl hexane and replace that with heptane. You guys out there in Zoom, I'll be signing off right now.